Welcome to today's class. So, having spent some time studying the full group of Riemannian isometries of the upper half plane, so having established that it is isomorphic to PS star L2R, and having shown that it decomposes as a semi-direct product of the group of Mobius transformations that preserve U bijectively with the two-element group. Let us go back to the upper half plane and say some more words about the geometry of the orientation preserving Riemannian isometries of the upper half plane. So, namely, we are going to say a little bit about the geometric behavior of the parabolic, elliptic, and hyperbolic Mobius transformations that preserve U bijectively. So, we're going to divide into cases. So as we will see, the main point will be to determine where the fixed point or points of our given Mobius transformation, of our given orientation preserving Riemannian isometry of U sit, right? So the main problem, kind of the key to studying the geometry of the Mobius transformation is to locate the fixed points. So let's start with a parabolic Mobius transformation. So that by definition it has only one fixed point in the Riemann sphere, in C bar. And now something to notice is that for any point we pick in C bar, the limit of the iterations of my transformation at that point always is always Z naught, right? So somehow Z naught, the fixed point, always attracts the iterations of the Mobius transformation at any point. So you can see this, say, let's say that take any translation, take any translation as we saw before, like one of these standard examples that we saw, and then take a translation. And then just compute the limit in C bar, right? Compute this limit in C bar, and for a translation, that limit is always going to give you infinity. And then just conjugate that here, and then of course the conjugating transformation of course lives in GL to C, not necessarily in SL2R, but it doesn't matter. So to carry the analysis on the entire Riemann sphere, and then just after that, after seeing this, then just keep it. Right? I mean, okay, but from this fact, we see then that the fixed point must be in R bar. Why? Because otherwise, so let's draw the x-axis. If the fixed point Z naught were, let's say, here in U, then for any point in here in minus U, in the lower half plane, for any point here, we see that this limit has to be Z naught. So at some point, some iteration has to enter from the lower half plane to the upper half plane. But then that means that then I can prove that nu does not preserve U bijectively. Right? Okay, so this argument shows that the fixed point cannot lie in U, and likewise it cannot lie in the lower half plane, because then you can apply the same argument but here, because then you would be able to pick any point in the upper half plane and then start iterating, and then at some point, because this limit has to be z0, you would have to land in the lower half plane, and then again you would have a contradiction, right? You would have that then nu does not preserve u bijectively. So it cannot be that that the fixed point is in u. It cannot be that the fixed point is in minus u. The only remaining possibility is that it sits in R bar. Okay, and once we know it sits in R bar, then there is something which is that given any two elements of R bar, there always is a Mobius transformation in PSL2R that takes that one point to the other, right, in R bar, which means that when you conjugate by this Mobius transformation that takes this point in R bar to the other point, this means that any point in R bar can be a fixed point of such a parabolic transformation, right? Because the type is preserved under conjugation, so you just conjugate by this one. So, okay, so actually we know that the fixed point has to be in R bar, but actually that we cannot refine any further, right? Any point in R bar can actually be the fixed point. Okay, now once we know that, we go on. We let's try to draw a picture. So here is R bar, and here I'm drawing the fixed point z0 of my parabolic Mobius transformation. And then, well, we know that since our transformation is in PSL2R, we know that the R bar is stable under all iterations of nu. Okay, so this means that somehow here one moves along R bar in either of these directions, right? And then one can see by seeing the picture we drew before. So maybe let me try and find it. By looking at this picture, right? One can easily be convinced that in the situation we are at here, when we take all the circles in all the Euclidean circles in C bar contained in U bar, so contained in U union R bar, and tangent to R bar at Z0, that is the circles that look like these four pink circles that I have drawn here. Each of those is stable under the action of nu, of all the powers of nu. Okay, so somehow the iterations of nu look like some sort of discrete flow on each of these, right? but somehow well organized in the following sense. Let's say for instance, okay, knowing that it's some sort of discrete flow, that the iterations behave like some sort of discrete flow. Let's say that the flow goes, let's say, counterclockwise along some circle, and hence along any circle of these pink circles, which, by the way, are then the horocycles based at Z0. Okay, knowing that, take any shortest curve of U passing through Z0. Right? So I know that somehow Z0 being in R bar, it does not really belong to U, right? but this one as kind of as a segment of an Euclidean circle in C bar, that one I can think that it passes through Z0. So okay, so take that one, and then we know that nu is a Riemannian isometry. So this means that the image of this shortest curve has to be another shortest curve. Okay, so let's say that other shortest curve is this one. So that means that when you look at these intersection points, right? Their images on their nu then have to be these ones. Right? So that's what I mean, that somehow the flow is well organized, right? I mean, somehow the first iteration. Yeah. So the first iteration of these points then go here, right? And likewise, if let's say that the image of this shortest curve on their nu is this shortest curve, then the image of these points are these points of intersection with the corresponding horocycles. So this means that somehow the first iteration of the points goes here. These are the images of the original points under the first iteration. And then under the second iteration, then go here, right? So somehow, and that's somehow how the whole behavior goes, right? So somehow the flow is inside the kind of this discrete flow under iterations happens inside each horocycle, in each of these pink circles, right? And somehow whenever I take a cross section by a shortest curve, the image is also another cross section by a shortest curve. That's kind of the whole point. So this is how it's well organized, right? Now, what do I mean by a horocycle? Well, precisely a circle in R bar, a circle in C bar, contained in U bar, so in the union of U with R bar, and tangent at some point at R bar. Just like here, the point of tangency is here, the fixed point of nu. Okay. So for parabolic orientation preserving Riemannian isometries of U, for parabolic ones, the fixed point has to be in R bar, and once we know that the fixed point has to be in R bar, we know that the horocycles based at the fixed point are each of them is stable on their all integer powers of nu. Right, and we know how this sort of discrete flow given by the iterations, by iterating nu, are organized. Right. Okay, so let's go to the next case, the parabolic case. The hyperbolic case. Suppose we take a hyperbolic Mobius transformation that preserves U bijectively. Okay, and so it has exactly two fixed points. So let's denote them Z0 and Z1. So from the analysis we made when we studied the standard examples, we know that one of the fixed points has to be a attractor and the other one has to be a repulsor, right, or repeller. So let's say that Z0 is the attractor and Z1 is the repulsor. So of course this I can do by reordering Z0 and Z1 if necessary, right? Okay, so what happens is this, right? That Z0 being attractor means that for every point not Z1, for every point which is not fixed, let's say by nu, the limit of the iterations is Z0, right? And similarly, we know that the limit of the iterations of the negative powers of nu is Z1, right? So somehow the negative power, so that's where everything comes from somehow, from Z1. Okay, so we know that that happens, and this we know just from the analysis we made of the standard examples. Okay, and I claim that from these facts we can show that both Z0 and Z1 are in R bar. And actually, if you think about it, the argument is actually the same with which we proved that Z0 was in R bar in the parabolic case. So let's say, let me argue for this one, for Z0. So if Z0 is not in R bar, well, let's draw R bar, and let's divide into two cases. Let's say in the case when if Z0 happened to be in minus u, so in the lower half plane, well, take any point in u different from Z1, right? Fortunately, Z1 is only 1 point. So okay, so let's take a point in u different from Z1. Okay, and then apply this. Then at some point you have to enter the lower half plane. Contradiction. Right? So okay, next case, let's say that Z0 is in u. Okay, in that case, well, now go and pick a point in the lower half plane, different from Z1. Right? Fortunately, Z1 is only 1 point. So from this, we know that some iteration has to enter here, the upper half plane, and when it enters, then we see that nu also is not preserving u bijectively, right? Because it's allowing someone from outside to enter. Right? Okay, so we see that then that Z0 has to be in R bar. And similarly, I leave you this as an exercise. You see something you can. I mean, it's pretty much the same argument that works. Okay. Now let's go on to try to see a picture, a geometric picture of the behavior. So here are the fixed points, Z0 and Z1. Here I have not decided which one is which. And I have drawn some segments of the common circles in C bar that pass through both of them, right? So it's the segments of those common circles. Well, the segments contained in U, right? Or if you will, in U bar. Okay, because we know the transformation being hyperbolic, we know that those segments are stable under the integral powers of nu, under all integral powers of nu, right? So this one is stable under all integral powers of nu, this one as well, etc. So by the way, notice that among all such segments, all those segments of common circles, but the segments that are contained in U, among all of them, exactly one is a shortest curve passing through Z0 and Z1, kind of going from Z0 and Z1, even though Z0 and Z1 sit at infinity. Okay. And each of this, this is a shortest curve. It's usually called the axis. So maybe let me give a name. Give the name here. So it's the axis of nu. Okay. Now we know that the positive iterations of nu either go in one sense. They go in one sense. This sense would be if this one is Z0, if this one is the attractor, and this one is the repulsor, right? Or in the other direction, if this happened to be the attractor, and this happened to be the repulsor. Okay, so let's stick to this second case, where this one is the attractor, Z0, and this one is the repulsor, Z1. Okay, so we know that whenever I take a point, let's say here, its image has to be again on this curve. Right? So let's say that the image is this one. Let's say. Okay, and then what happens? Then something similar happens. Let's say here when I take this point on the axis, its image has to be again on here on this curve on the axis, right? Because it's stable on their or integral powers of nu. Okay, so I claim that it's this one, this point. So let's argue. So take the shortest curve, passing through this one, and orthogonal here. Let's say, yeah, take. In other words, it's take the shortest curve that passes through this one and is an Apollonius circle for this one, right? So remember that these 2 points determine a family of Apollonius circles in C bar, right? Okay, so this one is part of an Apollonius circle. When I apply nu, the image is again in another Apollonius circle, right? So having said that the image of this point is this one, the image of this one has to be the Apollonius circle that passes through this one, right? Which is this other shortest curve. And then, so you see again here, if I take a kind of a cross section of all these segments, but the cross section I take it to be a shortest curve, a shortest curve, but not any shortest curve, a shortest curve that is part of an Apollonius circle of the 2 fixed points. Okay, if I take one of those shortest curves and I take this cross section, the image is another cross section of the same form, that is another segment of Apollonius circle, and this is how the whole discrete flow, when I iterate nu, functions, right? So all of these points go to all of these points, and then the next iteration, well, it go, let's say, to all of these points, etc. Right? So all of this, all of this, all of this, right? So along all these stable curves, things flow kind of that's kind of the picture of how things flow, right? So of course, one of the things I'm saying is that when you take any Apollonius circle of these 2 fixed points and you intersect it with U, that intersection is a shortest curve. This I leave as an exercise. Okay, so we have now a picture of how the hyperbolic orientation preserving isometries of U look like. Right? Okay, and then let's go to the elliptic case. So now take an elliptic Mobius transformation that preserves U bijectively. It again has 2 fixed points in C bar. And what I say is that none of these points, none of the 2 fixed points belongs to R bar. Why? Because you see, think about the standard example, and then think, let's say, about the origin in the standard example, right? So no matter how small neighborhood of 0 you take, if you take a segment of straight line passing through the origin, its image, it's not stable under an elliptic transformation, right? Or even like say take any straight line and then take any arbitrarily small neighborhood of 0. The image, the only common point between the original straight line and the image is going to be the origin, right? So no matter how small you are here, how close to 0 you are going to get, none of these segments is stable. Right? That this is in the standard example, right? But you see, this argument that I gave, for sufficiently small, for arbitrarily small neighborhood, you can perform even in the non-standard examples, right? Or if you want, just conjugate everything and then see what I just did when the fixed point is 0. But then you see R bar cannot be these points cannot be in R bar because I'm taking a transformation that preserves R bar. Okay, so none of them belongs there. Okay, and then now let's take a matrix in SL2R. I mean, what matters is that it has real entries, right? So it is possible to represent the Mobius transformation with a matrix with real entries. Okay, but now you see the fixed points are just complex numbers, and they have to be the roots, as we saw some time ago. They have to be the roots then of this degree 2 polynomial, right? Gamma is not 0 because infinity is not a fixed point. Why is infinity not a fixed point? Well, because these don't belong to R bar. Right? Okay, so this is a degree 2 real polynomial. It's a degree 2 polynomial with real entries. Hence, its roots are to conjugate complex numbers. So now I know that Z1 and Z0 are conjugate complex numbers. In particular, one of them lies in U and the other one lies in minus U. So any elliptic Mobius transformation preserving U bijectively has exactly one fixed point in U, right? So exactly two fixed points in C bar, but exactly one fixed point in U, right? Just similar to here, that the fixed points are not in U, right? So for a hyperbolic isometry of U, there are no fixed points in U, right? There are two fixed points, and the two fixed points lie in R bar. Okay, back to this elliptic case. You see now here, somehow determining that where the fixed points are, how the fixed points are organized was maybe a bit harder here. But otherwise, the behavior is again now it becomes really straightforward, because we know that somehow my transformation rotates the every Apollonius circle of the two fixed points, but the other fixed point is outside, right? All of those Apollonius circles are invariant under the all integral powers of nu, right? So if this is my fixed point, the integral powers of nu applied to any point kind of it looks like a flow like a discrete flow inside each of the Apollonian circles, right? So there's like some sort of discrete flow here and some sort of discrete flow here, and of course here I'm already kind of assuming that nu somehow goes counterclockwise. I mean, counterclockwise this way can also be thought as clockwise this way, right? So okay, so there's really no need of comment there. Okay, so if I take a point here, let's say its image I know is in this Apollonius circle of the two fixed points, so of this fixed point and its conjugate complex number. This I know, which by the way, notice that this circle has the fixed point as hyperbolic center, right? Because the hyperbolic center is a fixed point. So this distance has to be equal to the distance between the fixed point and the image of this guy, right? Which lies here, and so on, right? So actually one can show that that each of these Apollonius circles is a hyperbolic circle with hyperbolic center, this one. Okay, anyway, so let's see how this discrete flow is kind of coordinated or organized along different Apollonius circles. So for that, let's take any shortest curve passing through the fixed point. Let's say this one, and let's say that the image of this point is this point. Let's say, then, well, when I know that the image of this shortest curve is a shortest curve that passes through the fixed point, and the image of this one that I said was this one. So it has to be this shortest curve, right? So you see somehow it looks like as a rotation, right? Like this shortest curve is somehow like rotated this way, and then the second iteration that would look like something like again passing through the fixed point, and so on, right? So it looks like I'm really kind of rotating this shortest curves around this one. Right. So and something you see if you measure this angle, I mean the angle between this one and its image, right? That one is constant in the sense that no matter what geodesic you take passing through the fixed point, its image is going to keep the same angle with the original one as this one with its image. And actually that angle is actually is determined by the multiplier, which is a number, as you remember, canonically associated to the elliptic transformation. And the angle is actually has the property that the exponential of that angle, I mean, e to the I times that angle is the multiplier. Right? This can be seen very easily. Okay, what else? Something else. Notice if that angle is rational, well, if you will, a rational multiple of 2 pi, depending on how you are parameterizing the circle, whether with the interval 0, 1 or with the interval 0 to pi. The elliptic Mobius transformations has finite order, right? This we saw, and it's an if and only if. But otherwise, it has infinite order, and somehow one would expect that then if the elliptic transformation has infinite order, then what happens is that whenever I take any point, its orbit becomes dense, right? So this I leave you to think about that. Okay, and that's it for it. Another challenge would be to try to do this sort of basic analysis that I just did for the orientation preserving isometries, but for a for an isometry that does not preserve orientation. So this I also leave you to think about. I would say it's probably quite challenging. Okay, and that's it for today.